recording. Okay, so today our topic is the next one in the series solution method. The topic will be Bessel's equation. Okay. It will be Bessel's equation. If you remember that we have been, I think this is now maybe like 1, 2, 3. This is the fourth session actually on this series solution method. Okay, so we have started the series solution method from the simple power series, and then we discussed about the Legendre's equation. So the use of the simple power series was in the Legendre's equation. And then we, in the last week, in the last lecture, I introduced, and then even before that, I introduced the Frobenius method. So Frobenius method will be used in the for the solution of the Bessel's equation. So just to recall, the simple power series was this, okay? This one. And in the and in the Frobenius method, we use this type of substitution. Okay, so this is the difference between the simple power series and the Frobenius method. So simple power series we used in the those equations which were in which those functions were the coefficient functions were analytic. Whereas simply speaking, the Frobenius power series we use for those equations where the coefficient functions in the differential equations are non-analytic. So one of those equations is the Bessel's equation. So Bessel's equation is this, and this Bessel's equation will be used by the Frobenius method. So this will also exercise for the Frobenius method as well. So today I will try to solve with the complete steps. Last time in the Frobenius method, I skipped some step because of the time limitations, even though the time is also limited today, but I will try to finish it with all these steps. So this Bessel's equation is this: x square y double prime plus xy prime and plus x square minus this symbol which is similar to English letter V, but it is actually a Latin character which is called as the nu. So we will call it as a nu. So this is nu. So something similar to V, but it's not V. Okay, although it's difficult to type, so it would have been better if the book could use some other easily written symbol, but I want to follow the terminology of the book, so that's why I will use this nu over here. Okay, so nu can be any value, so maybe it can be an integer or it can be a non-integer value as well. Okay, so this is the Bessel's equation. So we have to find the solution of this Bessel's equation. So for the solution of this Bessel's equation, we can write it like in this format. Nu square over x square, and now if that means we have divided by x square throughout, and then we can write it like this. And then from here we can see that this equation, these functions, the coefficient functions y prime, coefficients of y prime and y, these functions 1 over x, and these are non-analytic. So for example, if for x is equal to 0, this is non-analytic. It is undefined, And for this one, it is also undefined, okay? Because it becomes 1 minus, that means over infinity, so it is undefined. But the original, in this format, the functions are analytic, okay? X is equal to 0, no problem over here, and X is equal to 0, no problem over here. But when we divide by X square, then these are the undefined functions. So we can say that we meet the conditions for the application of the Frobenius method. So in the Frobenius method, in this format, the functions should be for y prime and y should be undefined. So we can apply the Frobenius method for the Frobenius substitution. So for this Frobenius substitution, we have this y, the value of y is this, and we need to substitute y prime and y double prime as well. So for y double prime, we will put like this. So y double prime, we will put, I made a mistake. So for y double prime, we will put, because we will differentiate it for 2 times, so it will become m plus r into m plus, sorry, again, I make a mistake. So it will become sigma is equal to m is equal to 0 to infinity. It will be m plus r into m plus r minus 1 into am. So it should be am over here, and then x power m plus r minus 2. Okay. And then for the next one, because it is y prime over x, so 1 over x will be here. And then for y prime, we will put m is equal to 0 to infinity. It will be m plus r am x power m plus r minus 1. And then for the last term, we have this 1 over this. So 1 minus nu square over x square. And then m is equal to 0 to infinity, am x power m plus r. And then that is equal to 0. So we have substituted the Frobenius methods of substitution into the Bessel's equation. So now we can simplify it. So for the simplification, we can see that we can now simplify it. So for the simplification, now what we can do is we can now multiply this 1 over x by this, and then we can multiply this 1 minus nu square over x square by this. And then in this case, we will have the new form. So m is equal to 0 to infinity. So this term will remain the same, okay? It will be m plus r minus 1 into am x plus m plus r minus 2, okay? And then this term 1 over x will be done multiplied, so it will be sigma m is equal to 0 to infinity m plus r into am x plus m plus r minus 2, because it was x 1 over x, it was x power minus 1. So x power 1 minus 1 when go inside, so it will be x plus m plus r minus 2. Okay. Now multiply 1 with this, so it will be simply this term, m is equal to 0 to infinity am x plus m plus r. Okay. And then the second term is minus nu square, we keep it outside, m is equal to 0 to infinity. So this is x power minus 2. Okay, so x power minus 2, then when it goes inside, so it will be x plus m plus r minus 2, and that is equal to 0. Okay, so for this, now we can further see that all the terms have x plus m plus r minus 2, this first term, the second term, and the fourth term. But the third term has only x plus m plus x power m plus r. Okay, so we can change this by the change of the indices. So what we can do is, okay, we don't need to change this first term. This will remain same. And then it will be m plus r minus 1 into am x plus m plus r minus 2. And then the second term will remain the same. M is equal to 0 to infinity, m plus r am m plus r minus 2. Okay. And now for the third term, since if you remember that if I want to decrease this power by 2, I have to increase this index by 2. Okay. So in this case, then m is equal to 0 will become m is equal to 2, and then it will be, and then I have decreased m by 2, so it will be am minus 2. It will be now am minus 2, and then it will be x plus x over m plus r minus 2. And then the last one is minus nu square, m is equal to 0 to infinity, am x plus m plus r minus 2 is equal to 0. So now we can see that all these four terms have the same powers of x. But the only difference over here is here we have m is equal to 2, starting from m is equal to 2. But all the other terms are starting from m is equal to 0. So to also make it equal, what we can do is we can expand these terms, and then so that every term will be starting from m is equal to 2. So in this case, then that means we have to write the first two terms of this series. So when m is equal to 0, so it will be r. It will be then r, and then the next term will be r minus 1, and then it will be a0, and it will be x power r minus 2, x power r minus 2, because m is equal to 0. And when m is equal to 1, when m is equal to 1, then it will be r plus 1 into r, okay, into r, and then a 1, and then power x plus r minus 1. This will be x plus a1 x power r minus 1. Okay, so in this way, and then then there will be the sigma notation. So it will be sigma m plus r with it will done. Now this next sigma will start from m is equal to 2 to infinity, and then this term. Okay, so for the time being, I don't write it. Okay, I will consider it later on. And now for this, it will be m is equal to 0, so it will be r into a0, r into a0. And then x power, m was 0, x power r minus 2. Okay. And then I have is, okay, so, and then for the m is equal to 1, okay, m is equal to 1, so it will be r plus 1, and then a1, and then a power r minus, sorry, x power r minus 1. So it will be x power r minus 1. M is when I take m is equal to 1. So what I am doing is I am just taking the first two terms of these series. Okay, so that every series will now start from m is equal to 2. Okay, so this is already starting from m is equal to 2, so I don't need to change it. And how about this? This one I need to consider it like this, minus nu square. Then it will be a0 x power r minus 2. Okay, and then it will be minus nu square a1 x power r minus 1. Okay, x power r minus 1. And then okay, So now from each of these series, now m is equal to 2 to infinity terms are left, okay? Okay, and then I can now write like this plus the rest of these sigma terms, okay, plus rest of these sigma terms from m is equal to 2 to infinity, and then so on, whatever, and then that is equal to 0. Okay, so actually I am now more concerned with these terminologies. Okay, so in this case, now what I get over here is that some of the terms are with the x. I get how many terms? 1, 2, 3, 1, 2, 3, 4, 5, 6. I have got 6 terms. So half of these terms are with x power r minus 2, and the half of these terms are with x power r minus 1. If you see over here, okay, so this means that I can now collect these x to the power r minus 1, okay, x to the power r minus 1 terms, and then also the x to the power r minus 2 terms. So first of all, I collect these terms for the x to the power r minus 2, r minus 2. Okay, so and then these are and the terms with x to the power r minus 2 are with the coefficient a0, a0, a0. Okay, so I can also take it as a common. Okay, r minus 2 and then a0, a sub 0. So it will be now r into r minus 1. Okay, and then plus r minus nu square. Okay, and then plus the term with the x power r minus 1, a1, and that will be equal to r into r plus 1 plus r plus 1 minus nu square. Okay, and then for the equality of this equation, okay, and then we plus this sigma terms. These sigma terms we will consider separately, but this should be 0. That means what we can say is that the terms, the coefficients, this first part should be 0, okay, for the equality, and also the second part should be also 0. So this we can write it down in the next one. Okay, so I will write it down again, this x power r minus 2 in the next one, in the next slide. So from x power r minus 2, what we get is r into r minus 1 plus r minus nu square and times a naught should be equal to 0. Okay, so for the definition of the Frobenius method, a naught cannot be taken as 0. Okay, for the definition of the a naught cannot be taken. So if a naught cannot be taken as 0, then this term in the bracket will be 0. So what is this? R square minus r plus r minus nu square is equal to 0. So which gives us like r square is equal to nu square, or r is equal to plus minus nu. Okay, we get r is equal to plus minus. So we get a value of r which is plus and minus nu. And then from here, from the second one, x power r minus 1. And then we get it like this, r into r plus 1 into r plus r plus 1, okay, minus nu square into a1. That should be equal to 0. So now we know that a naught should not be 0, and r, the value of r is equal to minus nu. And what is nu? Nu is the, if you see that, what was nu? Nu was the part of the Bessel's equation. So nu has a finite value. So for example, if we consider that uh, r is equal to nu and which is not equal to 0, if you take nu which is not equal to 0, so r1 is equal to nu and r2 will be equal to minus nu. So in this case, uh, the expression in this cannot be 0. So for example, if I simplify this expression, so it will be r square plus r plus r plus 1, and nu square is equal to r square, so r square minus r square, and then it is equal to 2r plus 1. So since we know that r is equal to nu, so which is not equal to 0, this expression in the term in the bracket is not equal to 0. But for this whole expression to become 0, then we have no other choice than to assume that a1 will be equal to 0. So which means that a1 will be equal to 0.
Sorry, I have a question.
Yes.
So if we can make a1 as a 0, and let's say that we would have like a2 and a3, would it mean that they will be like how to say periodic function, periodic sum? Because if one sum is equal to 0 and next coefficient is not equal to 0, and it should be repeating, yes? Uh,
No, it's not like repeating. So what we have
okay.
now is said that a1 is equal to 0, and now we will prove that a3, a5, and a7 will be also equal to 0. So remember that I skipped that part of this equation sigma this. Okay. So now I will
Yes.
this part of the equation. Okay. So if I use this part of the equation, so then we can sum up these terms. Remember that we have changed the indexes from m is equal to 0 to m is equal to 2. So all the indexes are now m is equal to 2. And now we can sum up these coefficients. So these coefficients will be now m plus r and m plus r minus 1 am. So this will come from here. Okay. So
Yeah.
only thing is that m will be now start from 2. Okay. And then similarly there, and then we will write it like this. So and then now all these summations are from m is equal to 2 to infinity. And then the next one will be m plus r am, and then the next one will be am minus 2, and then the next one will be minus nu square am. There will be only 4 terms because originally there were four summation points. Okay, from there. So now, and then that is going to be multiplied by x plus m plus r minus 2 is equal to 0. So in order for this equation to be 0, so all of this thing inside should be equal to 0. And we can write it like this. So there is a little bit of simplification, not very difficult. So we will write it like this. Okay, am minus 2 and divided by m plus r square minus nu square. Okay, and since we know that r is equal to nu, so one of the solution is r is equal to nu. So if we put r is equal to nu over here, so then this will become am minus 2 over m into m plus 2 nu. Okay, so this will be the recursive relationship. So how this recursive relationship will work? So for this to be a 0, okay, so then m minus 2 is equal to 0, which means that we will start from m is equal to 2. Okay, and then for m is equal to 3, it will be a relationship with a1, right? So for example, if here it has to be A1, then it should be A3. Okay. And because now A1 is 0, so A3 will be 0, which means that that is equal to 0. Similarly, A5 will be equal to 0, A7 is equal to 0. So all the old subscript terms will be, odd subscript terms will be equal to 0. Okay, so the only terms which will remain over here will be the even terms. So A naught, A2, A4, these terms will exist. And all of these terms can be expressed in terms of A naught. Okay, so this means that we will only have the even terms in the solution over here. So for the even terms, it is easy to simplify it. Okay, so for example, since now we know that in this recursive relationships, all the terms are even, so we can further simplify it. Okay, so let me write it on in the next slide. So the recursive relationship was am is equal to minus am minus 1, sorry, minus 2, divided by m into, let me write what was that,
M plus
m into m
m
plus 2 nu. So m into m plus 2 nu. Okay, so since now we can see that all of these terms are even, so what we can do is, for simplification purpose, we can replace m by 2m. So instead of 2m, we can write 2m, and then here am, with m we can write 2m, that will be m 2m minus 2, and then it will be 2m into 2m plus 2 nu. Okay, and then it will be a to m will be equal to a 2m minus 2 over it will be 4m 4m into m plus nu. So this will be the simplified recursive relationship. Okay, so by taking a few of these terms of this recursive relationship, this relationship can be written in this generalized form. Okay, so a to m will be equal to then minus 1 to the power m a naught over 2 power 2m m factorial into uh, nu plus 1 and then nu plus 2 and then up to nu plus m. Okay, so in this case, this type of form of the relationship is called as the Bessel's coefficient. It's called as the Bessel's coefficient. Okay, so using this Bessel's coefficient, we can write the solution of the Bessel's equation. So remember that the general solution is this: y m is equal to 0 to infinity, m is equal to 0 to infinity a m x power m plus r. However, since we are now taking only the even terms, so we can write this equation, this solution like this. So just replace m with 2m. So it will be a 2m x power 2m plus r. And r we know that is equal to v. Or
shouldn't we take it as nu or minus nu?
hmm?
Will it be it's nu or minus nu, or we take it as a
Yeah,
value is equal to
minus
zero?
nu is the will be used in the other solution.
Ah, okay.
Yeah, minus nu will be used in the other solution. So in this way, then the solution, the first solution can be written like this: y1 of x is equal to x power nu. So now we can take x power r outside, okay, because r is equal to nu. So we can r1 is equal to nu and r2 is equal to minus nu. So first we are using the r1, okay. So x power nu we can take outside, and then it will be the actually it was sum of this, m is equal to 0 to infinity. So 0 to infinity, it will be minus 1 over our m a naught 2 power 2m m factorial into nu plus m into nu plus l. Okay, just give me a minute. Okay, sorry. So y1 of x. So and then that will be equal to then because here it will be now x power r we have taken outside, so it will be x power 2m. Okay. So this is called as the Bessel's function. Okay, in terms of nu. Okay, and this is called as the Bessel's function of first kind, okay, of order nu. Okay, Bessel's function of first kind of order nu. And similarly, if the second function with which use x power minus nu can be written like this: m is equal to 0 to infinity, and it will be minus 1 power m a naught 2 power m factorial into yeah, it is the same as nu plus m, and then it will reduce to nu plus 1. Okay. So these are the Bessel's functions of first kind of order nu, and then x power 2m. So this which means that if you remember, just like in the Legendre's equation, we found the Legendre's polynomial. So Legendre's polynomials are also the Legendre's function. Polynomial is a function. Okay, so polynomial is a function. So since we use the yeah, we found in the Legendre's equation, we found the Legendre's polynomial or Legendre's functions. So in the Bessel's equation, we also found a kind of function which can be written in some kind of this standard form. So this kind of standard form for the Bessel's function is useful. And then Mathematica also provides the solutions for these Legendre's for these standard forms. Okay, so the Bessel's function can also be written in terms of the in terms of some more simplified form in the case of a gamma function. Okay, in the case of gamma function as well. So, for example, Legendre's equation in terms of the gamma function can be written like this. Uh, Here, okay, uh,
Sorry.
yeah, is it clear?
I have a question. So,
Yes.
when we are writing the in the last steps, when we write the solution, in denominator v plus m multiplied to with the reduction to v plus 1. Can we just write it as a factorial of v plus m, like v plus m factorial?
Yes, we are actually going towards that. So simplify.
Ah, okay, okay.
Yeah, I'm actually going towards that simplification. So actually, for simplifying this expression a little bit further, it has been proposed that it has been because a naught is a arbitrary constant, so we can take any arbitrary value which is useful. Okay, so it has been proposed that for the simplification we can take the value of a naught equal to 1 over uh, uh, we can take the value of a naught is equal to 1 over 2 power uh, n uh, n factorial. Okay, where so very where n is actually same as nu. Okay, so we replace nu with n. Uh, why? The reason is we want to just differentiate the integer and non-integer solutions of the Bessel's function. So if nu is integer, then we use nu is equal to n. Okay, so if we take this substitution over here, so the Bessel's function for the integer n values can be written like this. Okay, x power n. So where n is same as nu, uh, m is equal to 0 to infinity minus 1 power m x power 2m 2 power 2m plus n m factorial, and then this now this term now becomes in one factorial term. So instead of for example many terms which are being multiplied, this term becomes a single factorial term. So factorial term. Okay, so this is for the case when nu is integer. Okay, so for more generalized okay for more generalized new values which includes also integers, there is another form, and that is given in the form of a gamma function. Okay, that's given in the form of a gamma function. In that case, the substitution is made like this: a naught is equal to 1 over 2 power nu, and that is the gamma function nu plus 1. So in this case, the Bessel's function in for any integer or non-integer value of nu becomes x power nu, uh, m is equal to 0 to infinity, and then minus 1 power m x power 2m 2 power 2m plus nu m factorial, and then this is the gamma function of nu plus m plus 1. Okay, anyway, these formulas are quite complicated and difficult to remember, but anyway, so this is the more generalized Bessel's function of first kind. Okay, in today's topic we have just considered the first kind Bessel's functions. Okay, there are also second kind Bessel's function, but I think for this course I am skipping it because we don't have enough time. And but anyway, for it will become very easy if you will perform these calculations using the Mathematica. Mathematica has all those inbuilt functions, and if you just understand the basic concept, then it is very easy to perform those calculations on Mathematica. So for the Mathematica part, I will also provide some tutorials later on. So, so today we have discussed about the Bessel's function. Okay, so two cases of Bessel's function we considered. So, for example, when I say that it is a uh, j0 of x, so it will be a Bessel's function of first kind of zeroth order. When I say j1 of x, so it will be the Bessel's function of first kind of first order, and then so on, something like this. And for any non-integer format, so we will use this formula in which a gamma function will be used. And what is gamma function? This is also a question. So gamma function is a function which is defined like this. Gamma function is defined like, so for example, if we take the gamma function of 1 plus nu. So this function is defined by this integral from 0 to infinity e power minus t, and then t power nu dt, where t should be greater than sorry, nu should be greater than minus 1. Okay, greater than minus 1. In fact, we also mentioned a little bit about gamma function in the Laplace transform chapter. Okay, so in this way, the gamma function is defined, and gamma function has some certain properties. So for example, gamma function of 1 is 1. Gamma function of 1 plus nu is equal to nu times the gamma function of nu, and so on. With this, we can determine. And similarly, so it will mean that gamma, if we take some integer values, okay. So for example, if we take some integer values, so gamma function of 1 plus n, where n is an integer, it will be equal to n factorial. Okay, so n factorial will be equal to gamma function of 1 plus n. 1 plus. So actually, I'm not sure whether gamma functions were taught in the calculus course or not, but here,
No,
no, yeah, but
no, we didn't fully cover.
brief
We are,
introduction of the
yeah.
gamma function. Okay, gamma function is just simply this integral anyway.
So it's basically the complex factorial for the non-integer values, as I got it.
Yes, this is the factor. Yeah, gamma function is actually used for finding the factorial of the non-integer values. So this is the main purpose of devising the gamma function. Okay. So for example, if we take the gamma function, can then tell you that gamma function of 1 by 2, that is equal to under root pi. Okay, gamma function of 1 by 2 is equal to square root of pi. So with this case, we can even find the values of the 1 by 2 factorial as well. But I think you can look for more information over the internet. There are very useful resources for that.
Okay.
Yes, gamma functions. So yeah, I think yeah, that's all for today. Yeah, this topic is a little bit complicated, or sometimes a little bit confusing as well. But the main thing is that if you try to understand how the Frobenius method was applied and how we collected these terms, then it is easy to understand this final function. And in the end, later on, once we have devised the formula for these functions, we only have to use this formula to find the solution of the similar differential equations. So
Okay.
a revision of this type of methodology later on when I will upload the video, that will be very useful to understand it better.
Yes. It will be. I guess it will be better to see it with the example than uh, in theory.
Yes. Okay. Let,
Okay. Thank you. Goodbye.
let me save this and save these slides, and now I can stop the share. Okay, that's all for today. If you have any questions, just let me know, or you can ask me later. Okay, that's all. Bye bye.
Goodbye.
Bye.
Goodbye.
Bye.
Goodbye.